All right. Natalia, I'm going to let you take it away. Natalia is at the University of Cambridge, and she's going to talk about unconventional computing with light, and also give a little bit of overview of unconventional computing with polaritons, which Lagoudakis is going to talk about. And she is already unmuted. I would ask everybody else to turn off their video at this point, and we will go from there. Okay, thank you. Go ahead. Are you still muted? Right, I will figure out how to unmute you. It says I have to ask you to unmute you.
Can you hear me?
Now we can hear you, yes.
Oh, okay, brilliant. Okay, thank you, David. Thank you everyone who logged in from all the various places you're in right now. I'm going to talk about unconventional computing with light, which has to do with everything that has light in it: optical, lasers, polaritons as hybridization of light and matter. And I will ask some questions. So the main topic, the main focus of my talk will be actually asking questions and directing, showing some weak points of everything that we're trying to propose. So by light, again, I will, I mean optical laser polariton systems by unconventional computing, using this system to simulate Hamiltonians, or even better, find some ground states of these Hamiltonians. And I'm a theorist, so I would like right away to say some acknowledgements to experimentalists that I was very lucky to collaborate with to implement some rather crazy ideas. So early work on polariton lattices was done with Jeremy Baumberg in Nanophotonic Center in Cambridge. We formulated the concept of using polariton graphs for minimizing XY Hamiltonian with Pavlos Lagoudakis at Skoltech. This work has continued with Jacqueline Bloch and Alberto Amo using polariton micropillars, where we're trying to achieve the remote coupling, which is very important if the actual machine wants to do something useful. But I'm indebted also to my theory team that I will mostly refer to the work done with my PhD student, Kirill Kalinin in Cambridge, and also some work done with another PhD student, but from Skoltech, Nikita Stroyev. So the goal of what we're trying to do, or many groups around the world are trying to do, is to use some kind of hybrid quantum analog digital platform for solving hard optimization problems, and do it by exploiting some physical properties of various systems. So optimization problems implies that we're trying to find some global minimum of the function of many variables, so function of functional that lives in high dimensional space with a lot of local minima, and finding the global minimum, the best decision, the best solution is always, is often a very hard problem to do. So what we're trying to achieve is to find a solution faster than conventional computing for a given precision, or find a better solution for a fixed time, or to solve more complex problems for a fixed cost for limited resources. And to do that, first we need to be able to map the original problem onto the language of the physical system, which is often connected to the spin Hamiltonians. That's what the physical systems are realizing often. So given a real-time optimization problem that can come from any kinds of areas, from planning logistics, from making new materials, from artificial intelligence, etc. So what we do, we minimize this function subject to perhaps some constraints in terms of the variables, many variables. So this is the highly dimensional function. So what we do, what we hope to do, is to map these variables into spins. And by spin, for instance, I can mean the phase of the element of my physical system, and to map the structure of the function into the couplings that coupling strength that connect the different elements of the physical system. So in this particular example, I map my problem into the classical XY Hamiltonian. So given the interaction strength, the coupling strength Jij's between spin I and spin J, I'm trying to find the configuration of spins that gives me the global minimum of this functional. So in this particular example, the spin, the phase is the angle that can be anything between 0 and 2 pi. It's possible to have some constraints and limit these phases onto binary sets, so 0 and pi, so the spin becomes cosine theta, so plus or minus 1. Or it could be other discrete system, the clock Hamiltonian or pot Hamiltonian. And what we know mathematically rigorously, that it's always possible to do. It's always possible to do this mapping. And what is good with only polynomial overhead on the number of variables. So in other words, given the original set of variables, I increase my new set of variables by only as a polynomial. But of course, this polynomial can also be quite huge. The overhead can be quite huge. And then we can exploit the correspondence between condensed matter systems and the language of complexity theories and optimization problems, because universal spin Hamiltonian becomes really NP hard problem to minimize. Quadratic unconstrained binary optimization, this is just minimization of the Ising Hamiltonian. Quadratic continuous optimization, minimization of XY Hamiltonian, and we can talk about higher order problems, higher order binary optimization, which can be mapped into local Hamiltonian quite naturally. So once we make this translation into the spin Hamiltonian, now we can think of building the physical system that has this element. Each element is associated with a new variable, new spin that we're trying to find. And then let the physical system arrange these couplings, Jij, between different elements, and then let the system to do the magic, somehow find a way to find the global minimum, or at least explore the low energy part of the spectrum for this Hamiltonian. But of course, to do that, to do something interesting, indeed, we have to have this principle, the principle that allows the system to find the global, not just the local minimum. And this is rather crucial in this construction. But also, once we have this physical system, let's assume that it does this minimization, we can ask the question, how do we describe the system mathematically? Because if we captured this, this principle, then we can run these algorithms, base our algorithms and run them on classical computing, from time to time asking the physical system to do the bottleneck for the classical computer, to do something that physical system can do faster. So, and that creates some kind of hybrid, that creates some kind of interaction between the classical computing and the speed up given by the physical property, using the natural physical properties of the system. And indeed, this program has been very actively pursued, especially in the last really few years, starting with perhaps Coherent Ising machine by Yoshi Yamamoto, and then using injection locked lasers, using optoelectronic systems, using electronic systems, or photonic lattices, photonic Ising machines, using lasers in a cavity. And we also contributed to this program by proposing to use polaritons as the basis for this physical system. But the questions that we need to ask on these new platforms as they come at almost daily basis, so there are several questions that we actually have to be thinking hard. So first of all, every system that appears, it has to justify the principle of its operation. So if the system finds the global minimum, we really need to understand that it does that. It does it in reality. Because there are many principles of minimization that physical system can exhibit. It could be physical annealing, it could be a adiabatic principle and its quantum analog known as quantum annealing, least action, minimum entropy generation, variational principle. But we know from practice that still more often than not, the physical system tends to go to the local minimum rather than global one. Okay, but now if the claim is made, if we have a system that has the potential to actually find the global minimum of the spin Hamiltonian, how do we validate the system? How do we know that it actually does what it promises to do? If a new system comes and the result is that based on 20 elements, on 20 spins, the global minimum, the ground state of the Hamiltonian is found in 80% of the cases generated from for max cut, for let's say for Möbius ladder, do we know that this system at least does what it proposes to do? Does it really minimizes what it proposes to do or not? Or if you have different systems, how do we compare? How do we compare different systems that have different interactions, that uses different graphs, different matrices, different coupling matrices? How do we compare between them and with different number of elements? Because the performance that these machines show vary. Some use sparse, some use dense interaction matrices, weighted or unweighted models, different distribution of the weights if it's weighted model, with and without transverse magnetic fields, using planar or non-planar geometry, using regular or non-regular graphs, etc., etc. So how do we compare? And then the final question, because this meeting and and my talk is mostly focused on this optical laser light systems. So what advantages do we actually have, if any, in comparison with other systems proposed? So I'm going to talk all these optical systems, the gain-dissipative systems. They set by balance of gain and dissipation. And the main principle by which the system is expected to find the global minimum is the minimum losses. So it was formulated by Yoshi Yamamoto for optical parametric oscillators like 7 years ago, about the same time. Neil Davidson formulated also this as a principle for the laser solver using the laser cavities. And then we also noticed that our system, the Polariton system arranged in lattices, also minimizes the corresponding Hamiltonian, spin Hamiltonian. As the gain rises and then something interesting happens, like a laser coherence or the formation of the boson Einstein condensate, it happens when the system can form the coherence, can form the Bose-Einstein condensate. And that means that it has minimum losses, minimum decay for the particular number of modes. And that, in contrast with classical annealing, when there is a thermal excitation that takes the system from the local minima, hopefully the system then finds the global minimum, or different from the quantum annealing, quantum adiabatic computing, when the system is prepared in a ground state and then slowly varies. Here we have the gain, we have the parameter, and we bring the system up until it hits the point where the condensation or coherence can get formed. And other lattices also have been used, and I'll just mention this Polariton micropillars, very promising lattice where the connections and the remote connections in particular can be established. Polaritons and trap lattices where the condensation occurs away from the point where the condensates were excited, or photon trapped condensates that Jan Kleijers will talk about. But what is the common between all these different systems is that the element, the bit of this computer, is the phase of the complex amplitude. So each element in all these systems is described by the complex number or complex function that changes in time, and it has amplitude and the phase. So the phase in this case is our variable, is the bit of this new computer, so to speak. Okay, and since I was asked to give a little introduction to Polaritons, and I will base some of my, of course, analysis on Polariton systems as one example of this unconventional computing system with light. In semiconductor, they exist in semiconductor microcavities where light couples to matter efficiently. So the experiment consists of thin layers of various materials, gallium, arsenide, aluminium. And the layers are made in such a way that the light of a particular frequency is trapped. So as the lasers shine on this semiconductor microcavity, the exciton is being excited. The exciton is in excited state, so it spits out the photon. And when the Bragg mirrors, with the Bragg mirrors, photon gets reflected, excites exactly the same exciton, etc. So the photon is re-emitted, reabsorbed, re-emitted, etc. And that creates the superposition of states, part light, part matter, known as polariton. Polaritons have small mass because they're partly light, about 5 or 4 orders of magnitude lower than mass of the electron. But due to the matter component, they strongly interact in systems. Photons bounce back and forth, but they escape the microcavity, given a short lifetime of just 10 picoseconds. But even on this very short lifetime, the thermalization takes place. By growing more and more mirrors, this estimate 10 picoseconds can be increased by a couple of orders in magnitude. Polaritons are bosons, and they condense at the relative warmth of cryogenic temperatures, 10 Kelvin in inorganic microcavities, and it can be taken to the room temperature in organic microcavities. And so in this favorite diagram, perhaps from the first paper that reported the Bose-Einstein condensation of polaritons, the experiments that I'm going to talk about use continuous wave excitation at this high energies, so that the polaritons scatter, the free carriers scatter, relax, and form the Bose-Einstein condensation at the bottom of this so-called lower polariton branch that appears from the hybridization of the phonon and exciton part of the spectrum. And there is a dissipation that counted by the short lifetime of these particles. What is important also to understand, therefore, that we can create, using spatial light modulator, we can create a single condensate by exciting with some laser light. But first, the non-condensed hot exciton reservoir of hot excitons is created, and then this reservoir relaxes, creating the condensate. But unlike equilibrium condensates, there are fluxes. It's a gain-dissipative system, so there are constant fluxes even for a single condensate that carry the particles away from the center where they are created and away from the excitation. They propagate with a fixed velocity characterized by the wave number, characteristic wave number that depends on the intensity of the pump, on the structure, on the width of the pump, and on the lifetime, on all the parameters of the system. So how do condensates interact? And here I will invoke again this principle of minimum losses, because the coupling mechanism consists of the stimulated relaxation of polaritons to the phase configuration with the highest occupation. So in other words, if I have the two condensates, then they will decide, depending on the distance, depending on the density of this condensate, they will decide whether to have in-phase configuration or out-of-phase configuration, depending on which density is the highest for the given configuration. So the first condensate, the first pair condensates will be created at the phase difference that maximizes the total mass, the total occupation of these two condensates. And then to see that, we can just write down the total mass in the system as a total density, so the square of the amplitudes of the wave function that characterizes the entire system. And then we can approximate this wave function as the sum of the wave functions of the individual condensates that have individual phases theta I. And then if I just write down this expression, I'll see that then I have, if I have n condensate, then I have n times the mass of isolated condensate, and then plus the sum of the couplings times the cosine, the difference of the phases between them, where the couplings are simply this sum of the product of the wave functions that are formed at different positions in my lattice. And therefore, to maximize the mass, this part is fixed. So maximizing the mass means I'm maximizing this expression, which is nothing less than just the the XY Hamiltonian. So we're minimizing the negative of this expression. So we're minimizing the XY Hamiltonian. And this expression, the coupling strength, can change the sign. So this integral can have different sign. It goes as a Bessel function, as a function of this product of the outflow wave vector multiplied by the distance between the condensates. And this has been supported by experiments done by Pavlos and his group, where two condensates, and you see the density of these condensates, were placed different distances apart from each other. So if I vary the distance, so initially at the distance of about 3.5 microns apart, you can see from the density image that this is the destructive interference. So the condensates are in outer phase. As I keep moving these condensates, now it's constructive in the middle, so the condensates are in phase. I keep moving, and again, the sign of the interaction change. So I'm moving along this line when the J changes its sign, and therefore the phase difference changes in such a way that it minimizes the XY Hamiltonian. And that has been taken, so then as a proposal of the Polariton graph simulator. So how to build it, you map matrix elements into coupling strength, as I previously described, arrange polaritons in a graph, let polariton condense, and then read out the phases, and that allegedly should be the minimum of the XY Hamiltonian, which has been verified for simple matrices of 4, 3, 5, etc. elements, up to some regular matrix with equal couplings. All the studies was motivated by what was previously done for in optical lattices. But now let me present now the next order of understanding what happens in a system, because I presented this minimum loss, and so far I didn't take into account any microscopic or any dynamics of the system. So I go back to this description of each condensate as the complex function, complex number that has amplitude and a phase, and now look at the time dynamics in this network with coupling coefficients Jij between different condensates. So the time evolution will have, and this is rather generic equation for many systems, lasers, optical or polariton, any gain-dissipative system with non-resonant excitation. So first of all, I need to have gain, the gain process that increases as during the operation of the system. So it's non-resonant excitation. The system is gain-dissipative, it has dissipation. So there are linear and non-linear losses. Non-linear losses in elastic scattering, something that gives the gain saturation of the system. There could be self-interactions within each node. Polaritons are strongly interacting, so they have this term. Lasers would not have this term. And then I have this coupling Jij, where coupling ith element with j element. And then, also important, the system has some noise. It could be quantum noise during the Bose-Einstein condensation. It could be classical noise, classical fluctuations. So if I had a simple function, simple element, just single one, and then I increase the gain from 0 slowly in time, then there would be bifurcation. So initially there is no occupation, and then there is this Hopf bifurcation. And if I maintain the gain at the constant level, then the occupation of my single node will also be kept constant. But then if I have a system of this gain, of these oscillators, and let's assume there is a fixed point for the system, then the fixed point will satisfy, so the density, the square of the amplitude, will be given by this expression, and then the evolution of the phase will be given by this equation until the fixed point is reached. And now you can see that indeed I have something, I have minimization that looks like minimization of the XY Hamiltonian, because this equation looks like a Kuramoto system, and for these terms responsible for the self-frequency, and this term resembles the Kuramoto oscillator. But the couplings in this case at the fixed point will be modified by the densities of the different nodes, that I do not know until my system finished its operation. So therefore, we minimize the XY model, but the couplings are modified by densities that are not a priori known. And this is the big problem now. Big problem for any coherent Ising or XY machine. To overcome this problem, we need to drive all the amplitudes to a fixed pre-postulated density occupation. So if I set this if I ad hoc set my process so that I have to, each node has to reach some threshold value, rho threshold, then I have to introduce this feedback in my system that measures occupation and modifies the gain at each particular mode depending on whether the occupation of the ith mode above or below this rho threshold. And then if this is done in the system, and we looked at what we have as a total mass in the system before, all gains were the same, and that's the equation that we would solve it close to the fixed point and at the fixed point. But if now we require, if we drive each gain independent for each element, then we replace then each density at the fixed point becomes equal to rho threshold, which cancel this term that modifies our coupling. And now we have the total mass that we know in advance. We have n elements, and we drove every element to rho threshold. So this is given, this is also known. And then if we find a way to always minimize, to always choose the gain in minimum way possible, so inducing as little gain as possible in our system, then this term therefore will be maximum, and indeed close to the threshold, we have Kuramoto oscillation that drive the system to its minimum. And maybe I'll show this little visualization of this process. So here we have 20 condensates, every condensate coupled to all the rest with random strength. And as we increase the gain to the linear dissipation, you can see that some of the elements shoot off. They have the occupation that it exceeds our goal. So we start decreasing the gain for those elements. And then at the end of this process, indeed, the fixed point is reached. And this is the minimum of the XY Hamiltonian. We can extend this to Ising Hamiltonians by adding on the top of the non-resonant pump and adding the n equal to resonant pump. So we need to pump at twice the frequency of the condensate. And this term leads to the projection of our phase onto 0 and pi. So, and in this case, the same logic applies together with this feedback when we have the total mass that we know ahead of time. It's just n times the threshold for the density. And if we minimize the gain we put in our system, we're going to maximize this expression, which is an Ising Hamiltonian, because this becomes the penalty on thetas that deviate from 0 and pi. And again, close to the threshold, it gives the parametric Kuramoto networks, indeed bringing the true minimum of the system. So what about coherent Ising machine? So far I talked about the Polariton condensates, and coherent Ising machine is the machine that is based on the long fiber and the optical pulses that propagate with equal spacing between them. They are squeezed and they interact in the latest experiments. They couple through FPGA with the use of the classical computer platform. But here we have only parametric pump, and it has to be equal strength for all the elements, and therefore it cannot be used to control the gain for each individual node to make all the densities be the same. So, and this is the problem. The density heterogeneity problem is a problem for the system. But there are some problems where it can be overcome. But what's important for this machine is then as the process goes on, the quadrature on the real part, the cosine survives, and it's gradually projected, therefore, on the spins that are plus or minus 1. And so the operation of the coherent Ising machine can be described by this equation where x is a real function. And this process of the squeezing actually gradually brings x to the plus or minus 1. But therefore, this is very similar to the Hopfield tank networks, studied and first introduced in 1985 in the context of the neural computation. So this is how these networks were formulated. Here again, we have some gain, and we have some elements that are projected. So Vj's here are spins that takes the value of xj and use this kind of a sigmoidal function to project it on plus or minus 1. So this is very similar to what coherent Ising machine actually performs. But if we write down what this Hopfield tank system minimizes, it actually minimizes the Lyapunov function that is written in this form. So the first term is what expected. This is the minimum. If Vi and Vj are plus or minus 1, then this energy has the minimum of the Ising Hamiltonian. If we minimize E, we minimize that. But we also have this extra term that depends on these integrals of our sigmoid function. And if tau is not small or G is not sufficiently step-like, then this term actually imposes an unknown magnetic field, transverse magnetic field, onto this Ising Hamiltonian. So actually, the Hopfield tank for sufficiently small tau, unless tau is very, very large and these terms doesn't contribute, does not minimize the Ising Hamiltonian. It consistently makes a mistake approximating this term. But still, it was quite successful in finding the minima of the network. So what happens? What is the principle of its operation? If I write down this J in terms of the orthonormal basis with eigenvalues lambda I, and then V in terms of this basis plus some null component, because some of the eigenvalues can be degenerate, then the energy can be rewritten in this form. And now I can see that the Hopfield tank algorithm changes amplitudes Vi's in a way that gradually favors the larger positive eigenvalues lambda I. So the Hopfield tank algorithm finds the minimum of the Ising model that corresponds to the largest positive eigenvalue. So in other words, the minimizers of the Ising Hamiltonian that simply read the sign of the largest eigenvector that corresponds to the largest eigenvalue. And coherent Ising machines are often tested on problems where such a minimum happens to be the global minimum. And now I will illustrate this on one very popular example, because often these coherent Ising machines are tested by solving max cut problem, just finding the cut whose size is at least the size of any other cut. So given the graph, we're trying to, for instance, in this case, divide the nodes into classes so that the minimizes the number of edges that go between elements that belong to different types. So the beauty of this problem, because it's formulated as minimization of Ising Hamiltonian, we know that it's NP hard, and even approximating this problem is very hard, is NP hard in general. A favorite example is to use unweighted 3 regular max cuts, so exactly 3 edges that come in from each node that connect any 3 nodes, and use it on non-planar graphs, which again we know that it is NP hard. But we know that it's NP hard in general, but the testing of the machine takes place on the particular graph connectivity. So some of the popular graph choices, it could be Möbius ladder, which is depicted here. You have only neighbors interactions arranged in a torus, and only some of these connections are flipped. So that's why it looks like the Möbius. Or another way to represent it, when you have, again, all the elements are in a circle, and there are three couplings of equal strength to the neighbors and to the one opposite to the node. This is non-planar graph for the unweighted three regular max cut. It's a very popular platform that many people use. It has known ground state energy, 3n/2 - 4, because only two edges would be violated at the ground state. For the general optical parametric oscillator, in 21% of the runs, the ground state was found. For optoelectronic networks, reported the success of 34%. For the electronic, it was 3%, etc. Another popular graph that people test their machines is Matisse spin glass. That was done for testing photonic Ising machine. Spin glass on torus for the digital annealers. Sherrington-Kirkpatrick model of spin glasses, so everything connected with everything with randomly distributed weights, etc., etc. Okay, but if we look at these matrices, we will see that actually they are not hard, and that the minimum will be found by simply looking at the sign of the elements of the eigenvector that correspond to the largest eigenvalue. And even the system that doesn't formally minimizes the Ising Hamiltonian, but satisfies this criteria, will find the solution. So, for instance, in this simulation, we took the Hopfield tank system and made it very bad. So it's a very gradient sigmoid. And at the end of the simulation, we have spins that vary in magnitude by almost 1,000. And then we project them on ±1 and see if this is the answer, if this is the minimizer of the system. And indeed, it turns out that it is. As long as we give enough time iterations, the Ron model finds the global minimum of the Möbius ladder. And it's a simple model, and therefore, any coherent Ising machine, any machine that claims that it solved the system, should at least do as well. But even if it does well, if it finds the ground state, it doesn't tell you anything about whether it's capable of solving any hard problems, because the Möbius ladder is very easy. And it has this property that favors the natural operation of the coherent Ising machine. What about other graphs? So here, this picture summarizes many other graphs that are typically used in testing coherent Ising machines. So here I plot the problem size, the number of spins. I generate 1,000 matrices per each model. Some of them are unweighted. Some of them have Gaussian or bimodal distribution of the weight. And then I have different symbols to represent different types of graphs. In 100% of these popular choices for evaluating coherent Ising machine, all these instances turned out to be easy, which means that the minimum of the Ising Hamiltonian simply corresponds to the signs of the eigenvalue of the eigenvector that correspond to the largest eigenvalue. And all these instances can be solved with very simple Hopfield tank iteration, even though we know that it does not minimizes correctly the Ising Hamiltonian. Another thing to note is that for some of these models, actually the complexity increases. Nevertheless, for small problem sizes, we still have at least 80% for the problem sizes less than 20 would give you the false good solution. So another conclusion of the coherent Ising machine gives you the success less than, say, 80% for the size 20, most likely doesn't even solve anything. And even if it reports this success, it means that probably it's still not proven that it will perform well on really hard problems. So what to do in this case? What to use as the test? And in order to decide that, we need to, first of all, to understand that the use of Möbius ladder, for instance, is made so that, first of all, it's a simple connection, simple connectivity that people can establish. So the connectivity should not be too hard. We can't say that take the random graph, 3 regular marks cut with all the random connection. We know that it's NP hard. But instead, we can actually probe the complexity. We can actually smoothly go from something which is easy to something which is truly hard. And we can start, so this is the procedure that we propose. We start with Möbius ladder, and then we randomly start rewiring. So first we flip 2 random edges, interchanging the connection between them. And as we increase the number of these rewiring edges, we move from Möbius ladder, from something which is very simple, very straightforward to optimize with any of these optical machines, to 3 regular graphs that are known to be NP hard. And you can see, so now I start rewiring these edges for the different number of elements in my system. And you can see this very rapid exponential growth of complexity. I started with something very simple. And then with already 5%, the Hopfield tank would not be able to find the global minimum. As I start increasing the edges at about 40% of rewired edges, I reach the full complexity, full NP hardness. So this graph was generated using another technique, the exact Groby solver, that in here I plot the time it takes to reach the 0 optimality gap. So when the ground state is truly reached for the system. So in other words, instead of the Möbius ladder, use Möbius ladder with few edges rewired, and that should take you continuously to more complex problems that are not, therefore, that do not have this very simple optimality structure. Okay, so in other words, in summary, so which questions to ask when the new machine is presented? So the first question, does the system minimize anything, even the local minimum? Does it find it? You've seen an example of Hopfield tank. It has the wrong Hamiltonian. Another problem that may occur when system would not minimize anything is complex coupling. And again, it's very notoriously happening in optical systems because often the couplings are complex. They could be Josephson coupling, they could come from external potentials, they come from the kinetic energy of interaction when there is a geometrical coupling, when it is coupled by proximity. And that gives either wrong minimum, or if the complex part of the coupling is too large, gives oscillations. The fixed point, the minimum will never be reached at all. So, and to see that close to the threshold, the presence of this complex part of the coupling actually appears as a phase lag, as this extra term in the sign. And if this term is small, it shifts the fixed point away from the minimum of the XY Hamiltonian, or Ising Hamiltonian if the spins are projected with resonant pulse. But if this term is large, then instead of the fixed point, you'll have a persistent oscillation. The system never settles. The second question to ask, is there anything in your coherent Ising or XY machine that brings the global rather than local minimum? Or in other words, can you address the sufficiently hard problems that cannot be solved, let's say, in polynomial time, and therefore can be easily solved for any dimensionality by classical computer? Another thing to keep in mind, how many elements have been used to demonstrate the performance of the machine. If n is small, then performance for small n is not indicative of performance for large n. So, and we know that often these coherent Ising machines start with very small number of spins, and then the general projection is made. But at least mathematically, the system that describes your system should show the behavior for the large number of spins on solving these problems. So At this moment, we do not have a system that actually proved that there is any advantage to use these machines for solving the hard problems. We seem to be close to this goal, but we are not there yet. And I don't want to finish on this kind of dim note, especially at the beginning of the meeting. So I would like to say a few words about the advantages of this laser Polariton simulators. We have a lot of controls in these systems. We have gain, we can change amplitudes, we can change the coupling. So we can use these controls to explore the large hyperspace and therefore look for the low-lying, at least low energy minima, and then perhaps find the true global minimum among them. So for instance, if again I write down this general statement for the total mass as written as the total injected gain, and then linear losses, and then this XY Hamiltonian. If I can find a way to keep the total gain the lowest possible while I'm exploring this space, then sooner or later I will hopefully find the true global minimum of the XY Hamiltonian. And there is some indication that actually the amplitude dynamics helps to avoid being stuck in a local minima. And that was shown in this experiment done by Neil Davidson when he arranged the lasers in a circle with ferromagnetic couplings between them, and then observed whether or not the quantization, if there is a phase winding around the circle that forms during the laser coherent state. And it turns out that if he just uses the Kuramoto model, then even for 10 elements, there is a large probability to have this phase winding during the coherence formation. So the Kuramoto model really finds the local minimum. Whereas when the amplitude dynamics, the laser dynamics was taken into account, then it was only for 10 elements, it was 100%, the probability of finding the true ground state that correspond to the ferromagnetic couplings, all spins up, was 100% for small models, and then gradually changed, but at least still staying significantly lower than the local minimum. Finally, I mentioned the complex coupling switching, complex coupling that prevents the system from finding the true minimum, or even making the oscillations in the system. But this can be curse, but this could be blessing. If we have control over the complex coupling, for instance, by introducing the external potentials between the elements, we can turn these couplings on and off, and then this would actually help to span again the hyperspace, very much in analogy with heterogenic computing idea, when you switch your trajectories to go from one saddle or from one saddle to another through the through these different orbits in your space, and therefore exploring different parts of the hyperspace and hopefully then finding a minimum in the neighborhood of a new point. And we showed, for instance, at least numerically, that indeed it gives some advantage, especially for even harder problems when you have the higher order binary optimization, and therefore you're trying to minimize k-local Hamiltonians. So it's possible for small networks, it's possible to actually bring the trajectory to always find the global state, and even for the large number of spins and large number of tensor elements, we still have the improvement, perhaps not as dramatic as for small n, but still an improvement over the success rate of finding the global minimum. But what are the challenges? So, there is some hope, and there is some control that we can exercise to actually make the system work, and indeed teach them how to find the global minimum. And therefore, the short-term challenges really to build these systems, establish the couplings between any two nodes independent of the rest of the system, go beyond the nearest neighbor coupling, to find a way to do fast amplitude and coupling adjustments. Because what I didn't mention, but what is crucially important, is that the coupling strength in these optical laser polaritonic systems depend on gain. And since we need to change the gain from node to node, it means that we change in the coupling. So we have to, from time to time, adjust the coupling, what we can control, to bring them back to the coupling that describe the original problem. And then, of course, the big task is how to find a way how to achieve the minimum total gain in the system that will guarantee that the system finds the true global minimum. And with that, I would like to stop. I will simply, again, thank my group. The main people responsible for what I presented is Kirill Kalinin from Cambridge and Nikita Stroyev from Skoltech. So thank you.
Okay, thank you. And virtual applause, I guess, here. Let me see if maybe if you stop sharing your screen now, then other people will be visible. Okay, so we can give you back the option to share that again. Okay, so let me remind people of the format for the Q&A. If you send me a chat privately, then I can unmute you and let you ask your question. And so I see a question here that's already come up. So I am going to unmute this person. Unfortunately, they do not seem to have an unmute possibility. They must have muted themselves. So I will read the questions here. Can you comment on the rate and time for the fine-tuning of the gain needed to ensure that a global minimum is reached? How will it scale with n? And actually, I had a similar question myself, which maybe I could pose this way, which is, it seems to me, at least in some of these schemes for the feedback, that you going to use a digital computer to run the feedback machine, and then aren't you somehow limited by the scaling of a digital machine at the end of the day, which is controlling the feedback for the whole system?
Yeah, so there are two parts of this story. Now, first of all, for general types of the question, indeed the feedback is necessary, I think, but there is a set of problems. For instance, 3 regular max cut has an unweighted max cut, right? So it has exactly three edges coming from each node, and they are unweighted. In this particular case, you don't need the adjustment, because by just the fact that you have the same coupling and the same number of nodes, you guarantee that all the densities will be the same. And this is what's been exploited by Coherent Ising machine of Yoshi Yamamoto. So for this type of problems, you don't need that. And perhaps the short-term idea is to actually test and to show the advantage on these graphs, because indeed, to control the densities, this is the bottleneck. This is the slowest part of your operation. Luckily, you don't have to do it like constantly. You need to do it from time to time during the operation. So it's not like you have to do it a million times. We calculated, and I think our estimation that we did just running the equations on a computer, that as soon as you do it for 1,000 nodes, you need to do perhaps 5-6 times the lower estimate to do this feedback, to do this adjustment, but you still need to do it. And here you have, usually you expect to do it with SLM, and it depends on the speed of SLM, right?
Do you have any estimates of the scaling of the feedback computation? So even though you don't need to do it every iteration, do you have some sense of how the feedback time processing scales with n the number of nodes?
Yes, yeah. So of course, this number that you have, so this time scales at least as a linear function with the nodes. But so it's
not. Know that? I mean, is that known, or is that still open?
This is just from our own simulations.
So sort of an empirical conclusion from doing.
But again, we didn't go into, we didn't double the number of nodes. It's just going between 1 and 2,000. We noticed that if for the 1,000 nodes you need, so the behavior may change, right? It may, exponential has very linear kind of behavior, and then it just shoots up, as we know from COVID.
Yeah. Okay.
I don't know, yes. But this is the bottleneck. If you need to do it, that will slow down your simulations dramatically.
Okay, another question. How large n should be tested in the lab? If small n does not indicate large n behavior, then how do you know experimentally when you've had a large enough n to test something reasonable?
This is exactly what this diagram showed. If you see, so it depends. Can I share the screen again?
I believe you can still share.
Mm-hmm. Yeah, this is exactly what this diagram gives you. Oops, sorry. Right, so first you need to choose, depending on your system, what kind of graph you can simulate. So what is the connectivity and how these connectivities are distributed. So there is a list of some of them here, right? So if you're choosing between those, you can see that their complexity changes, increases, right? For instance, if you've chosen to have 3 regular max cut, so this is this line with maybe, I don't know, weighted couplings, according to the Gaussian. So if this is the connectivity, this is the problem that you're solving, then that's what you would have. So if your machine, for instance, on 30 elements, on 30n, is capable of being bigger than this graph, let's say twice as big, then you're doing something very well.
Okay.
Right, it means better than what this easy instances tell you. You do it better than what could be done by at least hopeful tank, right? So even on this very basic test, you can say that.
Okay, so I'm going to let the next person unmute themselves. I believe they can do this.
Hi, yeah, can you hear me?
Yes. Okay, go ahead and ask your question.
Yeah, thank you. So my question is that the Kuramoto model that you showed, that one undergoes a synchronization transition if the coupling strength is larger than a threshold. So my question is, what would that imply for the actual exciton polariton system? And also, if you allow quantum fluctuations over the semi-classical dynamics there, how would that semi-classical synchronization transition manifest in quantum fluctuations?
Mm-hmm. Okay, let me again share the screen. Yeah, maybe here. Okay. So this is again the importance of having the same occupation per each node. So again, if I have this, if either the graph is such that I have all equal occupation, so again, equal connections, equal strength, the same number of edges coming from each node. So that gives me the equal occupation, or I'm implementing this feedback scheme. So if I'm implementing this feedback scheme, then all the densities become row threshold close to the the threshold, right? So which means that in the Kuramoto system, they all start having the same frequencies, right? Yeah. So therefore, there will always be synchronization. It's guaranteed because you have the coupling, and they all also all this density, all this term also approaches row threshold. So the cell frequencies also start taking the same values. So in this case, it's proven that, this always gives you the fixed point, and this fixed point is always the minimum of the XY Hamiltonian. Okay. Your second question about the quantum and classical noise. This is the big topic for discussion, because often these optical, this coherent Ising machine, coherent XY machine, our Polariton simulators, etc., are criticized because they are fully analog and there is nothing quantum. although we do not have in polariton condensates, we don't have a proof of any quantum speedup. And of course, when the Bose-Einstein condensation is created, the system is fully coherent. It behaves semi-classically. There is nothing, I mean, almost nothing quantum about it. But during the condensate formation, and indeed the search for the global minimum is when the condensate is not yet formed. So here we cannot exclude the possibility of some quantum speedup, of some entanglement that actually helps to span, you know, the hyperspace in search for the global minimum. But we don't know. We don't have any evidence for that in polariton system because it's just not much is done. You know, we didn't evaluated it from neither experimental nor theoretical part. So we believed it may be there, but more research is necessary to state for sure that there is a quantum speedup.
Okay, we have another question from Mark Ulrich.
Hi, Natalia. This is Mark Ulrich from North Carolina. I didn't recognize anything in there regarding disorder, and I was just wondering if that's a concern at all. I know that you know that screening can eliminate some of that. I also recognize that you're trying to see what is possible. So the idealized, you know, consideration might be the, you know, more of concern. But I'm sort of interested to hear more about how disorder might come into play. Yeah.
To tell you, this is a very good question as well, and to tell you the truth, this is the last of our worries at the moment.
Okay.
And there is a following reason. So if we have, so there are several ways how you can arrange the system, right? So one way to use the geometric coupling. So it's freely expanding condensates, and you know you arrange them in a graph. Particle, you know, there is a particle outflow, and this is how the condensates know about each other, and that's how they establish the corresponding phase difference. And of course, they exist on you know on a crystal, and crystal may break some symmetries. Although we notice that these the samples that at least Pavlos has in his lab are quite regular, so there is not much distortion of, you know, on the way of really, you know, scattering the obstacles and, you know, preventing the condensation. So he realized, you know, he had this the small lattices in different parts of the sample, and the state didn't change much. So they're quite regular structures because it's a superfluid system. So all the irregularities are often shielded by this superfluid behavior. But on the other hand, you can't go, I mean, it's not even, you know, you cannot go far with just playing with geometry in these systems, right? Because 3, I can of course put with any coupling strength, but where do I put the 4th one to have the coupling strength with the 3? You know, I can't do it on the plane. So we can't just play with geometry. To have something interesting, you really have to look hard into the remote couplings. So we would like to take the light from one condensate and put this light into another condensate so that they know about each other's existence and somehow arrange for the phase. Then disorder will not play any role because it's no longer the outflow of the particles. And that's what we're trying to do with Jacqueline Bloch and Alberto Amo. We try to use their platform with micropillars so that the condensates do not really interact geometrically. But instead use SLM to kind of trying to put the couplings between different micropillars. And then the defect is like in Yamamoto model. I mean, defect is not as prominently there as long as you can do this remote couplings. And you also need this to do this remote coupling, also to minimize this complex part of the coupling. Once you have the geometric coupling, you always have this complex coupling, unless you use the strap geometry where your condensate is separated. So you pump them, let's say, in the corners of the square, and the condensate will be created in the middle because it doesn't interact, because it's physically separated from the reservoir. Then the complex coupling hopefully will not be as prominent there. So I mean, these are even more concerns than the disorder of the sample per se.
All right, very good. Thank you very much. Nice work.
I think we have a question from Victor Golitsky.
Yes, thank you, David. Thanks, Natalia, for a great talk. So this is Victor Galitsky from Maryland. I have a general question. So you mostly have been talking about minimizing kind of Hamiltonians looking for energy minima. Have you thought about viewing the systems as simulators of dynamical systems, in particular chaotic systems? So it seems like you have a lot of nonlinearity and time dependence, which is kind of the usual ingredients in chaos, both classical and quantum. So is there something you're interested in?
This is a terrific question, because yes, we were looking into that. At this moment, we really understand that how rich our system is and what kind of states we can actually, we can have. So first of all, we can control, again, it has huge control in terms of the nonlinearity, in terms of these types of couplings, in terms of spin up, spin down, because from light, this system have also the spinel degree of freedom. So we can have all these very exotic, chimera states, kind of chaotic dynamics and control it very well. I didn't have time to talk about how we can actually have establish the dissipation and pump in such a way that we know what is the velocity profile of the system, for instance, right? There are very interesting questions that can be addressed. But so if what I don't know is what would be the practical application of having these very chaotic states. So the system can do it, right? It can generate the states, but first of all, for Polariton system, we usually see the average dynamics. So it would be rather difficult to see the actual time resolved dynamics of the condensates. It's possible, and there are, you have to have the right equipment probably to do that.
But for example, Kuramoto model that you wrote, it is a dynamical system, right? So it's primarily it's dynamics that is interesting. So how do you connect this statement with?
No, but maybe we should talk offline and
sure.
about it, because I would love to hear some interesting question that can be addressed. But why would I use this Polariton system instead of just simulating the Kuramoto model, for instance? I mean, it's I'm not sure what would the advantage of using the actual system be. Of course, it's super fast, right? And it's maybe the advantage still doing.
Perhaps one idea, I don't know if it's relevant, I'm not really an expert, but it sounds like cavity systems in general may allow for long-range interactions in particular, so kind of engineering interactions. And there are some prototypical quantum chaotic systems, such as recently, well-studied so-called Sajdev-Yakitaev model, which actually hasn't been realized anywhere else. So if you can engineer actually long-range systems, that might be interesting. I'm not sure if it's practical, but it's certainly fundamentally interesting.
That's again the problem with these systems being, once the condensation took place, you're already in kind of semi-classical regime. You don't, quantum non-commutativity of quantum operators doesn't contribute anymore to the dynamics. So it's really, once the condensation is formed, it's classical. So we wouldn't be able, unfortunately, to address any quantum questions or questions of quantum dynamics. I mean, if you go to a different limit, when you have a single polariton per lattice site, when the system is fully quantum, that system may be better suitable for this kind of analysis. But if there is the question, but for the classical system to address with this kind of system, that would be possible. So I would love to speak more about this.
Yeah, thank you very much.
Okay, so to stick to our schedule, let me first of all flash up again our schedule for today. Some of you may have come in late and didn't hear early on that one of our speakers, Lagradakis, had to cancel, although I've gotten word from him he will still be able to participate in the panel discussion this afternoon. So he will be free at that point. So at this point, we'll go on to the talk by Sanjeev Ghosh on quantum reservoir networks. And where are you actually coming from? Where are you sitting? Sajib?
Yeah, I'm working in NTU Singapore.
Okay,
And
so it's like the middle of the night for you, right?
Yeah.
Okay, well, thank you. Thank you very much for being with us. And this will be a half-hour talk. And again, at this point, if everyone else could mute and turn off their video. And any questions, send them to me by private chat on the Zoom chat feature, and I'll put them in the queue for questions after the talk is over. So what I'm going to do here, actually, let me say I'm going to stop sharing this. Okay. Now I'm going to stop recording and then start it again so that we have separate talks done here. Okay.